Yeah, thank you, Sanjeev, for your introduction, and uh, good afternoon, everyone. So thank you for inviting me. So my topic is to revisit drought and compound extremes. So just a snapshot of weather and climate disasters for the United States. You can see this is the in 2023 we have seen several billion dollars climate disasters. You can see they are everywhere, and mostly in the southeast US, as you can see, they're concentrated. So most of the loss are either in the southern part of US or southeast, typically in the Florida. Also in the California, we can see a lot of climate disasters. So my topic is related to drought. So we can see lots of economic loss related to the drought. And the number of events, if we look at this figure, we can see drought that occurs every month. And typically during the month of June, July, August, the percentage of area or the number of events increases. So how the drought progress? So it starts with the natural climate variability. Uh, and as a result of climate variability, the reduction in the precipitation, not only the magnitude, but the timing of the precipitation intensity. And because the high temperature, high wind speed, and low relative humidity and greater sunshine. So when this type of combination, they occur together, that lead to reduced infiltration, runoff, and percolations, and increased evaporation and transpiration. So the first part of the drought, that is on the meteorological drought, which is controlled by the atmospheric processes. So after the meteorological drought initiates, that lead to soil water deficiency or the reduced soil moisture that leads to affect the agriculture, crop yield. And this part of the drought, that is agricultural drought, and which further as time progress, so that leads to affect the stream flow, reduction in water levels in lakes, ponds, and so that part of drought is hydrological drought. So basically the drought progress with the time, meteorological, agricultural, hydrological, and sometimes you'll see a combination of drought that is occurring simultaneously. So all this affects the economic impact, social impacts, and environmental impacts. So that we call as a socio-economic drought. So unlike flooding, we cannot see the drought. So we rely on the different types of drought indices from SPI, PDSI, and SPEI, and multivariate drought index. So all these drought indices that we see, they are derived based on a combination of variables. Or for example, the SPI is a single variable. It's looking at the precipitation, whereas SPEI, that is integrating precipitation and temperature information in terms of PET. So if you're looking for the climate change assessment where the temperature plays a very important role, so SPI will be a better indicator than the SPI. And also we are, with the time evolution of the time, we are also implementing the multivariate drought index. So that's a combination of different types of variable. And basically this multivariate drought index is based on the multivariate statistical analysis using copula and different types of model, where we can see the dependence between different types of variable that is contributing to the drought. So I have few topics to cover in 20 minutes. So one topic is spatial drought propagation mechanism. So recently we have published 2 articles on this. So if you're interested, I can send you the journal articles. And so basically what we know so far, we know that we can use different types of hydrometeorological variables and drought indices for developing the drought prediction models, and we can rely on the teleconnection mechanisms and so on, sea surface temperature, so that can help in long-term drought prediction. And over the time, we have developed different types of models, statistical methods, probabilistic methods, and the neural network method, which was existing during 1995. Now the deep learning methods are emerging. And also we look at the hydrologic models and R system models. So different types of input that goes to different types of models. And as a result, we can look at the lead time, when the drought starts and terminates, how severe it is, and the probability of occurrence. So this is what we have been doing and we have learned so far. And this is an example of drought forecasting. So we have input data set, then we can, this is an example of hybrid model where we can use wavelet decomposition to generate soft signals and predict individual signals. And finally, we can add them and we can get the output. So by doing the hybrid model, as we can see here, we can improve the drought prediction at long lead time. So this is an example of hybrid model for drought prediction. So one of the key challenge is space-time propagation of drought. So this is one of the topic I have been working for last few years. So for example, if you see the drought that started on August 2013, and as the time progressed within the span of 6 months, we can see that the drought has propagated from spread over to a different part of the California. So question is, since the drought is evolving with the time as well as space, so can we capture this information and develop a more robust drought prediction? So we have highlighted this issue that spatial and interconnected structure of continental scale drought is one of the unsolved problem in hydrology. This was highlighted by previous studies. So to address this problem, we also explore the recent drought, how the drought evolved in space. For example, in April 2010, September, you can see the drought is evolving and spreading over the continental US. So we are interested to look at, can we capture the spatial propagation of drought? And how are the drought events regionally and globally linked to each other? And the drought synchronization or physical process that triggers the multi-continental drought. So this is what we explored in one of the articles. And to do the modeling, we rely on the complex network framework. So basically, complex network models, it's a powerful tool to describe the real world complex system. And these are built on graph theory and statistical physics. So using complex network, we can study the topology, behavior, and interconnectedness, then the synchronization and cascading behaviors. So this is an example of network where you can see that different nodes are connected meaningfully together through links. And this is an example of Facebook where global population are connected like individuals and through the links of friendship. And the complex network can be very simple and it can be complex. So when you're looking at the multi-layer complex networks, they are more challenging to develop. So this is one of the topics that we are exploring now. So few results. So spatial linkage among global droughts. So basically this plot you are seeing here, it is degree centrality, which basically signifies the number of grid that are experiencing simultaneous drought event within the lead time of 1 to 3 months. So in our study, we selected 1 to 3 month lag time, but this lag time can be increased to 6 months, and you can still look at some of the characteristics. So for this analysis, we use self-calibrated standardized Palmer Drought Severity Index, and we use nearly 119 years of data sets. And what we found is that some of the regions they're connected, that is driven by, there are two things. One is some are connected by local to regional droughts. So drought happens and that's slowly spread over the land surface. So there the land atmosphere processes are very, very critical for synchronization of drought within the land region. But when the drought is happening over the multi-continents, so basically it is driven by the large-scale climate indices, teleconnection, and also coupled with land atmospheric feedback and atmosphere ocean system. So, and also we found that the higher elevation over the land, so the droughts are kind of connected, but that's just a finding, but we did not explore why. So maybe in the future we'll explore that. So this is an example of degree centrality, how it can be used to look at the spatial linkage among global droughts. Then another thing we found out that the major global droughts, the multi-continental droughts, they form a rich cloth phenomenon. That means synchronous behavior of drought hubs when they occur together or co-evolve within a lag time 1 to 3 months. We call that as a rich cloth phenomenon. So like Western US, North and South Africa, and the Southwest Asia and Northern Australia. So these regions also tend to show higher complex network matrix. So to summarize, basically we can use different types of complex network coefficients or the metrics to study different types of global drought characteristics. So for this figure, we use connection density matrix, so that helps us to identify the tendency of a network to form a cluster. And the primary objective of doing this is because this work has direct impact on the economy and government, because if the drought happens over the global breadbasket regions, so that likely to trigger the global food security. So we are also exploring on those topics right now. And next topic I want to highlight is on hydrological drought. So it's a combination of how climate and catchment that affects the hydrological drought. So the climate, catchment, and hydrological drought. So basically this topic, I thought it is interesting because how the hydrological drought evolves over the landscape. So it starts with the water cycle that we see. It is quite complex, and the flow over the land is controlled by a combination of climate and catchment processes. So basically the hydrological drought is a result of nonlinear interaction between climate and catchment processes. So previous studies, mostly they use linear relation to study the climate and catchment processes. So we further explored how we can quantify them using the nonlinear relationship between the hydrological drought and combination of climate and catchment processes. So our key goal was how are the hydrological drought regimes clustered over the continental US, and what are the key climate and catchment characteristics that controls the hydrological drought. So this was the main question that we addressed in our article. So to address our question, what we did is we took 652 catchments over the US from the gauges to data sets, from different types of data set, and we selected 60 variables. Overall 60 variables for 652 catchments. So out of which there are 12 climate variables, example precipitation, temperature, and potential evapotranspiration. 15 catchment variable, that is stream order, base flow index, and 4 land cover variables, the percentage of different land cover types. 23 soil characteristics, that is very useful for the infiltration analysis, and 6 topographic variable. So we consider all these climate and catchment variables to study what exactly is controlling the hydrological drought. So this is the snapshot of the modeling framework. So we created the database, then we extracted the drought characteristics, then we found the clustering to identify the regions with the similar homogeneous behavior, and then we use random forest modeling and use some metrics, for example, minimal depth and interpretative partial dependence. So these metrics we use to interpret the results of the random forest algorithm. So what we found is we can classify the hydrological drought based on the selected catchments into 3 groups, and you can see here these are the 3 groups: group 1, group 2, and group 3. So in the group 1, you can see the duration is high, then intensity and number of drought events are low. So basically, to summarize, so cluster 1, we found there are 142 catchments, and these catchments see the drought duration that can go from 7 to 20 months, the low intensities, and for this drought, they look at the less number of events. So cluster 2, we got 242 catchments, and this drought we classified into moderate because the upper limit is 12 months. So this drought duration that varies from 7 to 12 months. And cluster 3 is 268 catchments. So these catchments see the short-term drought like 5 to 8 months, but they have got high intensities and higher number of events. So once we classify the droughts into different groups, our next step was to look at how different combination of climate and catchment variable that control the evolution of hydrological drought. So for that, we rely on different metrics. So one of the example is minimal depth. So this metric helps us to rank the climate and catchment variable that influence the hydrological drought. Basically, the green dots that we see, those are important controlling variable for different types of regions: regime 1, regime 2, and regime 3. So what we found is the base flow index. That's a very important variable because that controls the infiltration and which further takes the base flow to the stream flow. So that is more important in catchment regions, regime 1 and regime 2. But when you move to the next important variable, we can clearly see there are difference occurs. But for the regime 3, what we found is the monthly maximum number of days that measures the precipitation, that is a key driver. And hydrological group C, the soil group that has got slow infiltration rates, that also we can see that is controlling the hydrological drought. But there are a lot of other variables that controls the hydrological drought. So to summarize, we can use random forest modeling framework to identify different controls of climate and catchment over the hydrological drought. So another thing we explored is the functional relationship using partial dependence plot. So previous studies mostly focused on the linear or scatter plots to look at the relationship. So we went ahead and looked at how the drought duration and base flow index, they are connected for regime 1, regime 2, and for the number of maximum number of rainy days that is affecting more into the hydrological drought in regime 3. So we can clearly see the relation between the drivers and the hydrological drought. They are non-linear, and this information can be useful to constrain the models for the future work. So the next topic I will explore about compound drought and heat wave events. So over the past few years, we have working on CDHW events. So I will highlight some of the works. So one of the main motivation of this study is we look at the temperature anomaly from 1983 until recent period. And what we found is there is a positive temperature anomaly which is kind of increasing in the recent years. So we explored that how does an increase in temperature that affected compound drought and heat wave events across the globe, and whether the background aridity that controls the increasing compound drought and heat wave. So I will demonstrate some of the results. So before going to the results, so one of the potential impact of heat wave and drought is because drought has itself has significant impact. Heat wave, it has significant impact. So when we combine, the impact multiplies. So there's significant impact on heat stroke, on the health, and also the elderly population. And because of the heat wave, there are 70,000 deaths in 2003 heat wave in Europe. And people of economically backward, outdoor workers are more exposed to this event. And based on a study, that heat stress spike predicted to cost global economy like 2.4 trillion every year. That was one of the cited reference. So, and the other important application is drought and heat wave is during drought, the water in the reservoirs are low, and during heat wave, the energy demand is high. So to balance the water available in reservoirs and energy supply, that will be a challenging factor. So what we did is we look at SCP-DSI as our drought indicator and temperature as our heat wave indicator. So we merge or overlap this time series and identify the regions where we got the compound drought and heat wave events. So one of the key contribution we did in our study is to advance the temporal resolution. So in our case, the drought was at the weekly time scale, heat wave at the daily time scale. So that improves previous studies where they look at the monthly time scale for drought and heat wave event because they don't overlaps much in detail. And using those SCP-DSI and temperature information, we developed different daily compound drought heat wave severity. Then we found the event, severity of the event. So based on this information, what we found is the proportion of heat wave event that coincide with the extreme drought weeks is increasing over the time. So what we found is a significant increasing trend was observed during the recent period compared to the previous period. And the percentage of land area that witnessed a compound drought and heat wave event also increased simultaneously. So as temperature increases that we saw in previous slide, so the increase in temperature that also increasing the compound drought and heat wave events, and the percentage of area is also increasing. And at the global scale, we evaluated the changes because the positive anomaly of temperature between 2000 to 2016 minus 1983 to 1999. So what we found is the CDSW frequency. So what we found is recently we get 1 to 3 more events per year, and the duration has also increased. So Sanjeev, you are saying something, or?
Yeah, in the interest of the time, can you summarize it?
Yes. I will take few minutes. So the limitations and challenges for the drought, I will highlight few things. And so one of the challenges is the non-stationary climate. So because the drought indices, they are based on the distribution functions, parameters. So parameters will change over the time because of the non-stationarity. So that will affect the drought indices. And the baseline period, when you are comparing the drought with the baseline, so basically that is very important. So in ideal scenario, we should include the major historical drought event, and then we can have better information for the future. Then the climate indices, they disagree, often, and so with the rise in temperature, they are very sensitive to temperature. So that is also one of the things that we need to explore. Then the role of anthropogenic influence on the drought, so that is also affecting the drought indices as well as monitoring and prediction. So this is one of the important things I would like to highlight, that the lack of communication with the stakeholder. For example, we are saying Palmer Drought Severity Index to a farmer or to a reservoir manager. They really don't get into too much information. But if we tell that, okay, if the Palmer PDSI is less than -4, your reservoir level will be around 650 feet. So that will be more meaningful and for planning purposes. So to summarize, so drought and heat wave triggered by complex interaction between physical processes. So it's important to study those physical mechanisms and their impact on the socio ecosystem. So CDHW events, compound events, so robust forecasting tools are currently not in place. So this is another important topic. Then since the climate and catchment conditions are evolving or changing with the time, so the progression or the characteristics of the drought will also change. And existing drought indicators face several limitations. I highlighted some of these things. So with that, I think I'll stop here. So thank you very much for your attention.
Thank you, Ashok. So now we have time for a couple of questions. Go ahead.
Thank you for the presentation. It was very interesting. On the first portion where you're looking at the connection of droughts and the hubs and mentioned that this could be of interest for things like multiple breadbasket failures, is there a way to use this method to identify what might be driving those sorts of events or where the risk of those events are, or is it purely statistical in the connection of droughts in these regions?
Yeah, that's a very good question, actually. So now we are exploring. This is an ongoing work. So we have identified the global breadbasket areas and delineated, and so we are looking at how this risk likely to be connected and how they will evolve over the time. So statistically, that is correct that they are connected. Now we have to see their impact on those global breadbasket regions. And also the mechanism that is driving this multi-continental droughts. So we look at, it is not shown here, but we look at the El Nino and La Nina pattern. So that is also a driving force for the multi-continental drought, which is done in many studies. But going forward, I think we'll explore, can we predict the multi-continental drought? Now we know they're connected, but can we predict in the future? So to do that, we have to study the mechanisms in detail. So thank you. So did I answer the question? Or Weston, did
Yes.
I answer? Okay.
Yep, thank you.
Yeah, thank you.
Yeah, we have time for one more question. If nobody has, then I'll ask one question. So Ashok, you generated very high resolution, high quality data set, or as well as understanding. How these understanding can be used to improve climate model that we use to predict or forecast, or how these information can be used to kind of reduce uncertainties in the forecast, or forecast including projection.
Yeah, I think if we go for the finer scale, the vegetation, for example, the infiltration capacity, vegetation, and the land atmospheric feedback, because that is highly relevant, that is driving the drought over the land surface, like the one I shown for the California drought. So if you take more, coarse resolution, then looking at the spatial connectivity of drought, I think that will be difficult. So going forward, I think high resolution models can be very useful. Typically, the spatial prediction of drought and looking at the land atmospheric feedback. I think there's a lot of things to be done on that.
Okay, thank you, Ashok.
Yeah.